So I think we can start with the first presentation. So I can invite on the stage the first speaker, Amir Rahnama. He's going to present a paper titled "Can Local Explanation Techniques Explain Linear Additive Models?" co-authored with Judith Butepage, Pierre Gerotz, and Rick Bonstrom. The stage is yours.
Thank you. Hi, everyone. My name is Amir, and I'm presenting this work with my supervisor, Henrik Bostrom. We're from KTH in Sweden, and my colleagues, Judith and Pierre. Judith is at EA now, and Pierre is at University of Liège in Belgium. And our work is about local additive explanation. It's actually, we changed the title to fit the reviewer's taste. It's actually is about evaluating local additive explanation. So back in 2019, I wrote a paper and I saw some flaws with Lime. So we wanted to improve upon those problems. And we realized that we really don't think the way explanations are evaluated is rigorous. And as you can see, we started experimenting in February 2020. I've been rejected in so many conferences. And when I say reject, I don't mean like weak reject, I mean reject. So it's like 3 years of my research life was spent on this project. And I kind of feel like it must be very easy to follow because I worked with it for so long, but it might not be the case. So let's start by a very brief overview of what we mean by local additive explanations. We mean particularly explanations of methods like Lime and kernel. In these explanations, you have a black box model, F, and you have an input instance or explained instance, that is the X. And what you do is that you allocate phi j's, that is the importance of feature j, to an interpretable representation of X. It could be a superpixel, or it could be like a interpretable binary representation in the tabular data, right? M is the index for the number of features. So this is how it looks. So if you have 0.9 as predicted probability, it decomposes. If you have two features, for example, it's like 0.1 plus 0.8. And there is a lot of debate whether there's a geometric interpretation in terms of like local, like complex analysis local. In the first article of Lime, the authors said it's local. 1 year later, the same set of authors wrote the anchors paper. They said they are somewhat local. And a year after that, me and my supervisor wrote a workshop paper, and we proved that it's not local. So I want to emphasize that I am a bit hesitant to say if there is a geometrical interpretation here, right? But it looks like that. So how are explanations evaluated? So I have mentally categorized the way we evaluate them into 3 main categories. Either you use robustness measures, you don't have a ground truth. So what you do is that you nullify important and unimportant features. You use the model that you had to explain, you were supposed to explain as some sort of oracle, and you see whether the nullification of these features has any effect or not, right? No ground truth here. Sometimes you use synthetic data sets, something like this polynomial. You have like 2 weights here for x1 and x2. Once you generate your data set, you fit a model, a complex model on this, and then you get the explanation, and you expect that the similarity of explanation is close and similar to this W1 and 2, that lambda. And then recently, you have a third way to evaluate these explanations. The check mark is saying that I'm biased. I like these ones more than the rest of them. These are when we actually use an interpretable model. So we fool kind of the explanation. We say, explain this model. The explanation thinks it's very complicated, but it's not. It's an interpretable model. Usually in these works, before our work, the baseline, the ground truth, is basically the W. And you know that W is like a global explanation. So before us, they were using, most of the research, they were using the weights of interpretable model as a baseline for local explanation. So, yeah. And then we have the contamination studies. I'm a bit hesitant and critical when they, I don't know, change the model and they expect the explanation to find some flaws, or they change the data, they put a dog in the image of a bedroom, and they expect the explanation to kind of pick it up. I think it's a bit unfair to the explanation. I'll talk about this more. So you also have those studies. So robustness measures, like I said, they don't have any assumption on the data or model. All you need to do is to nullify and see if the black box is kind of predicting how much changes in the predicted score, right? So there are a lot of limitations. They're really popular, but there are a lot of limitations with these. First, is the model a good oracle? If you remove the tail of a cat and the model is used to seeing cats with tails, and now the model is confused and you're blaming it in Lyme, why are we blaming the explanation here? Also, how to nullify features. I've used these measures a lot. You nullify them with mean. They give you, Lyme is more robust than SHAP. Then you nullify them with median. Now it's the reverse. Like, there's no, we don't have a foundation, but they're very popular. Again, there's a consequence to this limitation. Who to blame? I think we're blaming explanation too much. When we have the synthetic data sets, we don't have a model assumption. You can use complex models. But then again, we're not sure if the model has learned what we expect the model to learn, so that we use the weights for penalizing the explanations. So here we also have the blaming problem, right? And the third method, the interpretable models. We can also use any data, but then we have the limitation that, okay, I mean, it's Lyme and SHAP are really good for linear models. So what? Are they good for neural networks? We can't really extrapolate here. So we also have this limitation. Contamination studies also suffer from these problems. But there's one thing that is different. Ground truth using interpretable models, because you're getting the ground truth from a model trained without contaminating it, you can blame the explanation, because the explanation should be faithful to the model. So that's why we thought this particular category of method needs to be improved. So I'm going to show you an example. So here I have the robustness measures and the ground truth for synthetic data sets. I'm actually using the Guidotti's work, Seneca RC. It's a very good paper. And also I'm comparing it with the ground truth using interpretable models of OpenXAI papers. So here we have the synthetic data set up there. And then we train a logistic regression. And again, these are not explanation, but these are the ground truth. Robustness measures don't have ground truth, but what we're doing here is that we're nullifying each feature for each instance individually. What we see here is that Seneca RC and OpenXAI fall into the problem that they use the same exact baseline for all the instances, regardless of the decision boundary of the model. You see, model has learned that X1 and X2 are important. That's why the decision boundary is not a vertical or horizontal line. But they're completely insensitive. So they're correct that both features are important, but they're completely insensitive to where these instances are, the notion of local. When you see robustness, it's even worse, because in robustness, in a lot of cases, the baseline says that the second feature is not even important. That's why you don't see any vector. The baseline vector is going to the Y. So this was how we started the project. So I'm gonna have to be faster now. So remember that FAX decomposed to that by the linear additive models? What if we found another linear additive decomposition from the model? That way, we could potentially take all these terms, because there's no interaction term, right? So take all these terms one by one, construct a vector, and use a similarity metric, very old school, to actually compare how far these additive decompositions are, right? So this is what we call the notion of local explanation accuracy. So where are these MIAS scores, model intrinsic additive scores? They exist in linear regression. You just need to take each of these WJ, XJs for each feature and use a similarity metric. It's nothing complicated, but we wanted to also have them for classification models. That we had to change something. We could not explain the predicted score. We had to explain the log odds, weight of evidence, because then we have a linear additive model. Then we have a linear additive function, and then we can construct all these little terms and construct a vector and use the similarity metric to actually see how far these additive terms are. So this is the MEOS scores now. You can see that they're different because they come from the model. This is a logistic regression again, same data set. Their model, they're different depending on where the instance is in the decision boundary of the logistic regression. Pay attention on the decision boundary where the colors are not that strong. They're very confused, which is great because that's where exactly the model is very uncertain and there's a lot of problems in the model. So they're faithful to the model. But I'm hesitant to say there's a geometrical interpretation. It's just stretching it. But they're different. They're local. So they don't fall into the trap of Seneca RC and OpenXAI, nor the fault of robustness. And they both have, in the MEOS scores, you see that both features are important. Okay. So we ran experiments. We thought, let's compare Lime and kernel SHAP with a non-additive explanation, assuming that the non-additive explanation is going to be very bad. And we thought that Lime and kernel SHAP are going to be amazing, explaining all these three models I mentioned, right? That was our expectation. In our paper, it's a very long paper, it's like 50 pages. We argued that Spearman's rank correlation is the best similarity metric. And we thought because it's a rank correlation, when we average it on the test set, because we get the explanation for each data set in the test set and we average them, it should be above 0.7 to be acceptable. I hope you can see this. These are our regression data sets. These are the average of explanation accuracy using Spearman's rank correlation on a lot of data sets. Both values are the best, most accurate explanations. The yellow data sets, they are the ones that LPI, that is non-additive, is beating the performance of the additive models. I talk about this a little bit later. But if you see the average, over 20 data sets, they're pretty decent, actually. I would say they pass the sanity check for linear regression. However, if you look at the 20 data sets of the classification, they're extremely poor. You have those two data sets, the LPI in both models is more accurate, but look at the averages, like 0.258 of Lime for logistic regression. These are extremely low numbers, right? I was very hesitant because I thought I'm introducing a measure and I'm saying these models, these explanation techniques don't work. So I redid the experiments from scratch, got the same result, and I realized that sometimes in some data sets, they're pretty good. Breast cancer, banknote, for both models. So I spent half of the paper, around 25 pages, understanding the factors that can cause this. So it's not that I'm introducing a random measure in 20 data sets and there's nothing makes sense. In some data sets, they're pretty okay when the number of numerical features, for example, is limited, if they follow a certain distribution, if the model is good in generalization. So there are factors. So the two most important questions that we couldn't really answer was, why is it the case that they are so good at explaining linear regression, but not for the classification model? We have two hypotheses. One is that the surrogate of Lime and SHAP are using linear regression models. So I think they match perfectly when they explain the regression models, but they are poor when they're explaining the classification models. For this, I suggest for future studies to change this, use linear classification surrogates for Lime and SHAP. Another important question is, why is LPI so good sometimes, especially for linear regression? I don't know. I think it's really weird. By the way, LPI is a method that was proposed in 2019 at ECML. It's a very underappreciated work, but it's in my slide. I will share the slides on the website. So this is I don't know why a non-additive model is better at finding additive decompositions than two additive models, even though LPI is permutation important, so it doesn't even have a model. So it doesn't have a surrogate model, but it's still better. So this is a very strange behavior, I think. Like I said in the journal track paper, we wrote a lot about factors that can affect explanation accuracy, and we came up with 8. Some of them are data related, number of numerical, categorical, correlated features, and even the pre-processing technique you use can severely affect explanation accuracy according to our definition that I mentioned, right? Model generalization is very, very important, but not that the larger the generalization, the better the generalization, the better the accuracy. It's much more complicated than that. Explanation sample size is very, very important. And our methodology also has a limitation that if you change the similarity metric, you get very different results. We all have like basically gone through all this. So yeah, you can read it in the paper. And lastly, we also investigate that most accurate explanations are not robust, according to our definition of accuracy, and vice versa. So yeah, I just want to say that the main limitation of MIAS, like I said, is that you cannot really say if they can explain linear models, they cannot also explain neural networks. And I think that's it because I'm running out of time. Thanks a lot for listening.
Thank you very much. So, questions from the audience? We should have 2 volunteers with microphones. We have a question there.
Hi, thanks a lot for the presentation. Very interesting work, and I think it's very important to evaluate explanations in this direction. Just, I was curious about the logistic regression example. I'm assuming that you use kernel SHAP on the predictions, so the probabilities which you end up with. You could also use kernel SHAP and Lime probably on the values which you obtain before you use the activation, so the softmax function. Have you tried this as well?
No, that's a good question, but I don't think I have. Also, maybe I wasn't clear that we actually pass in the log odds function to Lyman SHAP because you can ramp the prediction function. So Lyman SHAP actually see the log odds. So maybe that wasn't clear. No, I actually have not done that, but must be an interesting investigation actually, now that I think about it. Thanks.
Any other question? I cannot see the other microphone. Oh, here we have a question.
So both Lime and SHAP replace the variables with binary variables, essentially.
Right.
So how much of this issue comes from that process rather than the linear approximation?
That is a very good question. If you want a scientific answer, I don't have it because I didn't really experiment on this. If you want a non-scientific answer, I think that that's negligible compared to the way they sample this random sampling. I think you lose a lot of information binarizing and making an interpretable representation, but you lose much more when you sample, I think. But yeah, I should actually, yeah. I need to investigate this more.
Okay, if there are no other questions, I will thank the speaker again. I will reach you later for more questions.